Hi, I'm going to do a standing waves problem for you so you can see how we might go about solving one of these problems and hopefully come up with the right answer. So the problem for today that I'm going to solve, in a physics lab, a rope is observed to make 240 complete vibrational cycles in 15 seconds. The length of the rope is 2.8 meters and the measurements are made for the 6th harmonic standing wave. Determine the speed of the waves in the rope. All right, so our typical process, let's write down what we know, draw a picture. So we have a rope being shaken. Whee! I don't know, I'm just going to say it's tied to a table. There, my beautiful table, right? And we know that it makes 240 complete cycles in 15 seconds. The length of the rope is 2.8 meters. The measurements are made for the 6th harmonic. And the last thing is, what do we want to know? We want to know what the speed of the waves is on the rope. All right, so this is a standing waves problem. We're in the 6th harmonic on a rope. The rope piece tells me that we have a closed system. So we're going to do 6th harmonic, closed. We know the length, we know some weird information there, and we're looking for velocity. So we have two useful equations for velocity. Velocity is frequency times wavelength. And for a string or a rope, we've got velocity is the square root of tension over mass per unit length. I have length. I don't know anything about mass or tension. This is not going to be helpful, at least not right now. Let's see if this one's going to be helpful. Velocity is frequency times wavelength. Well, not very helpful either, but I can make a relationship between the length and the wavelength for the 6th harmonic of closed, and I think that I can get my frequency from this data. So what I'm going to do is say, well, the frequency is the number of waves or oscillations per second. So I know it does 240 cycles in 15 seconds. So I can get my frequency. And the frequency is 240 over 15, that's 16 hertz. All right, there we go. I now know my frequency. Ta-da! Looking for that. So I need to know what my wavelength is. So how do I get wavelength? This is where we draw the pattern of the wave for a 6th harmonic closed. Closed means nodes on both ends. So there's no motion there. So my wave pattern, okay, so antinode, there's my first node. There's my second, 3, 4, 5, 6. I think this is going to be my 6th. Let's make sure once I get my other part of the wave drawn. Okay, so wobble, wobble, wobble. That's my first harmonic. That's the easiest. Second, third, fourth, fifth, 6th. This is the 6th harmonic closed. So now we need to figure out how the length and the wavelength are related. So this length has how many waves? Go back to our rule, 2 full footballs is 1 wave. So I've got 1 wave here, I've got another there, I've got another there. So in this case, all right, the length is 3 wavelengths. Or the wavelength is 1/3 of the length. Because this is a full wave here, here's a second full wave, and here's my 3rd full wave. So you can either think of it as the total length has 3 waves, or 1 wavelength is 1/3 of the length. They both work, they both get you the same thing, they're the same equation. So I think at this point, we've got it. So we've got the frequency and we've got the wavelength. Velocity is frequency times wavelength. My frequency is 16 hertz. And my wavelength is, well, I better do the calculation, huh? So wavelength is 1/3 of the length. Oh, I should have made an easier number. 2.4 would be 0.67? No, 0.933 apparently. All right, so the wavelength is 0.933 meters. So that's times 0.933 meters. 16 times 0.933, we end up with 15 meters on top. There's a 1/seconds right there. We end up with 15 meters per second. And now that's fast. That's about 33 miles an hour. So you might say, is that reasonable? Well, this isn't a physical object moving like a car or something. This is the speed of a wave passing along a string. So if I just sent a wave pulse along this string or slinky, it would travel down at 15 meters a second, which is darned fast, but it's totally reasonable for a wave on a string. Zoom. Okay, good. So it's going to 3.8 meters, 2.8 meters. We could actually figure out how much time it took if we wanted. And there are questions like that, so you might want to think about how you might do that. Velocity is the change in x over change in time. If I know that the distance is 2.8 meters, I can figure out how much time it would take the wave to travel the entire length of the rope. So that's a basic problem using standing waves. You can see it pulls in a lot of different information because we have to draw, and based on the harmonic, we have to know what kind of standing wave it is. Open, 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 closed, closed, closed. We have to use this information. Remember that frequency is waves per second. And then we had to use our picture here and the knowledge that one wave is 2 footballs in order to make this relationship, so we could get that. So there's a lot here, but we were able to figure out the velocity of the waves on the string, and we didn't even have to use this equation. We used the easier one. Now, if we knew the velocity, we could go back to this equation, and suppose I told you the mass of the rope, you could figure out the tension. So there's a lot of other steps you can take once you've got this kind of basis down. So that's a basic standing waves problem, closed, closed. This was a 6th harmonic. Usually it's just 1, 2, or 3, or 4, but I wanted to show you a more complex one. So, good job.